Srijan, can you hear me?
Yes, I can hear you. Can you hear me?
Yeah, I can hear you.
Yeah, I think Srijan hasn't joined yet. So we will see. We'll wait for a few minutes and then we'll call him if he doesn't
Okay.
join.
Yeah,
Yeah.
that's fine. No worries. We have until the top of the hour to join. So
Yeah, sure.
just want to say thank you to everybody who has joined as a guest. If you do have any questions, excuse me a second. If you do have any questions, you can list them in the Q&A box located at the bottom of your screen or on the one second. Or in the chat box, whichever one is most convenient for you. We will be starting a little bit after 3 o'clock, and thank you. Thank you for joining.
Thank you.
Surkar, just so you know, I'll be in the background on audio and video mute, so if there are any issues.
Do not know me. I am Srikar Velichetti. I am the director for the Technology Serving Humanity Speaker Series for this academic year. Today, we are very fortunate to have Dr. Srijan Kumar from the College of Computing at Georgia Tech. So Srijan got his PhD from the University of Maryland, and he is a recent NSF Career Award recipient. His work has primarily focused on harm and hatred in online communities, and more specifically, the reliability and harm of AI. His research has been implemented practically. His models have been implemented in firms like Flipkart, which is India's largest online retailer, and the Birdwatch platform of Twitter or X. Okay. More recently, he's been working in safety issues in AI. So today, what Srijan is going to talk about is the interesting work he's doing on human-centered AI and security. So with that, Srijan, it's all yours.
Awesome. Thank you very much for the invitation. I am super excited to be here and present some of the recent work that we have done at my research group around human-centered AI for web integrity. This is a super important topic, primarily because, today we get most of our news and information from web and social media platforms, and increasingly also through large language model powered chatbots and online ecosystem and online services. However, when you look at online social media, when you look at large language models, not everything is as it seems. There's a lot of harmful content, bad actors, incorrect information, malicious things, right? Broadly, bad actors, bad content, broadly categorized out there. If you look at social media, for example, there's estimates by Facebook itself that says that around 145 million accounts on its platforms are estimated to be fake, and that's official numbers from Meta or Facebook. Um, Third parties estimates around on Amazon have said that there are fake reviews, and that to 300 million of them on Amazon. And given that it's one of the primary e-commerce websites that we get our stuff from, it's very important for us to know what's fake, what's not. And the problem is actually just getting started to it's getting worse and worse day by day now because of the information pollution that large language models have been able to create to do. It's so trivial now to create information. The cost of information creation has pretty much become zero. And that also means that the cost of misinformation creation has also pretty much become zero. So my research and all the misinformation, disinformation, either human generated or or AI generated, including things like deep fakes and audio fakes and others, have a lot of societal impact. Primarily, all the way from democracy and impacts to democracy, science, technology, as well as broadly this entire society. And since again we get most of our information from these digital sources, if you will, than physical sources, it becomes important for us to know how to fix it. So yeah, my research group at Georgia Tech deals with these issues in an end-to-end or holistic manner, starting from creating detection models that are natural language processing based, graph neural network based, and behavior model based. So we create detection models. We understand how reliable, robust, secure, safe these systems, these models are. That's a very big thrust for my research group. We also look at what impact these systems have, what impact AI broadly has on the society. And then we also create various different mitigation solutions on how to fix these issues that exist around online social media, around LLMs and others. And as Shrikar was saying, lot of our stuff is in production. So we'll get started with detection, and yeah, I love questions. So please feel free to put your questions on chat, and Shrikar has kindly agreed to convey those questions to me. So let's start with a few of our detection models and works that we have created, starting with multilingual detection. So why is multilingual detection important? Well, turns out that 74% of all the content online is actually not in English, even though we think it is. And most of our news and most of the and large fraction of the world actually does not speak English as their first or second language, right? Uh, Even though AI researchers and practitioners are very heavily leaning into English as the is one of the primary sources from on of language, but in fact we need to look at the multilingual aspects of all the technology that is being created. So my student Gaurav, for my he's is a senior PhD student in my group now. When he was a junior PhD student, he was super curious about multimodality and multilinguality. So he started this project where we're looking at if you create English classifiers to do some task, and if you using large language models, and if you create equivalent non-English classifiers to do the same task, again using large language models, are they comparable? How does their accuracy, how does their robustness compare, right? So that was the research question that he started with. And if he started out saying, if they are equally accurate, great. If not, if there is some disparity, how do we fix that disparity? So we realized that there's no multilingual data set. So what we did was we took a few quote unquote societally relevant data sets around crisis detection, fake news detection, emotion detection, and so on. And these were all in English. And you can see the statistics of these data sets. But what we did was, since these were in English and we were interested in multilinguality, we converted those into multilingual data sets. So we essentially, so each, let me clarify. So each piece of text, each piece of information unit in this data set had an image and a corresponding text, right? So what we did was we took the text and we translated those into 6 different languages, including Spanish, Chinese, Hindi, and a few other languages. And the translation was done through human translators, so native speakers, and then we tried a few automated translators, and then got a subset of those automated translations validated by these native speakers who said that these are very high quality. So then we used these automated translation techniques on the entire data set. And then what we did was, so that gave us a multilingual data set, right? So for each data set, now we have 6 copies, each with a different language. Even if you change the language, the classification, so this is a classification task. So the classification label doesn't change, because if something is fake, it's fake regardless of what language it is in. If there's a image and text that's saying it's reporting infrastructure damage, it's reporting infrastructure damage even regardless of whether it's in English or Chinese or Hindi. So we get this multilingual equivalency data set. So then what we did was we created these multimodal, then we created these classifiers using using state-of-the-art at the time LLM models, and said, if we run these state-of-the-art LLM models for each language, so we took the best performing model in each individual language and ran those and used those to do these classification tasks. We found that English models perform much better, in many cases 20% better than these other languages, right? So the languages of Spanish, French, Portuguese, Chinese, and Hindi. So the English model performed significantly better than non-English language models, right, on the same task. So the input is the same, just the language is different. And if you take the best models in each language, this is how well they perform, right? So there's a huge disparity that we discovered. So then we get to the point of how do we fix it? So in terms of fixing this, what we did was we said, okay, there are these images. So can we use them, right, as data augmentation techniques? So what we did was we took the text, we encoded those using BERT, because at the time BERT was the great thing. This was way back in 2021 that we did this research, right? And we took these images and we encoded them using VGG16, again, the popular system at the time. And then we combined the two and we said, okay, we have this data augmentation through image modality. And if we use a late fusion based multimodal model, how well does the system perform? Does it improve the performance? And if so, does it improve the performance uniformly? So what we found was that across the board, there's improvement, and there's 5% improvement in English, and on an average, a 11.5% improvement in non-English languages. So that's great, because that's essentially helping improve the reduce the gap between English and non-English languages. And it's still not perfect, still not like completely uniform. But what we are seeing over here is that by doing this sort of data augmentation, we are able to even improve the large language models being used to improve to do this classification. And we have repeated the study now. We have used the latest GPT-4 models, and we have done some more analysis, and we see similar trends, right? Where these multimodal models, these language-specific multimodal models, there still is disparity if you give English versus non-English content, right? So in fact, we have a paper that was just accepted at the web conference or the World Wide Web Conference. And there we looked at English versus Chinese versus Hindi medical question answering. And English was just much better than Hindi and Chinese. Right. So, and that we got that validated through like, medical experts. So there's a lot of disparity work that we have done around multilinguality, because I think, like, since most of the world doesn't speak English as a first and second language, it becomes quite important as LLMs become more and more pervasive and powerful. I'll pause here, take any questions about this part before I move on to the next steps.
As of now, I don't see any questions, so probably you can proceed to the next part. Yeah.
Okay, sounds good. Yeah. So far I've shown that, multilingual models can be improved by doing data augmentation, specifically around like multimodal data augmentation, right? And we have shown it for societally, quote unquote, societally relevant tasks, but you don't necessarily have to just restrict to that. You can try it on any task, and most likely you'll find this disparity. So we asked ourselves, okay, apart from this data augmentation, can we do something else? Can we look at building detectors using non-language techniques? And this was work that we did some time ago, but it has gotten a lot of community attention because we looked at the graph-based techniques to build great detectors, right? And our insight here was that if you are looking at graphs, and I'll give some examples of graphs, most of the real world graphs are in fact temporal, which means that, and here's an example. Let's say a user is interacting with an item. An item can be a social media post, let's say. So when a user interacts with an item, we can represent that as a graph where a user is a node, where an item is a node, and an interaction is an edge, right, between the user and the item. And that interaction has a timestamp of when that interaction has happened, and certain features and certain attributes about this interaction. And as time passes, as more interactions happen, more user nodes, more item nodes, and more of these edges are created. And these edges are all temporal in nature. They are happening over time. Right. So before our work, there were very few works that looked at this temporal nature of graphs. Right. Most of the works were looking at static graphs. So what we did was we extended that work, and we created these models, which I'll talk about, which work on temporal dynamically evolving graph. which are super important and super practical, because most of the real world graphs are temporal in nature, right? And this is a graph foundation model, if you will. And this is super crucial, because now whenever there's data that you can represent as temporal graphs, this model can be used. So in our experiments, which I'll talk about, we use this type of graph representation to identify fraudulent users on e-commerce platforms, on social media platforms, and others. But you can look at you can look at knowledge graphs, and you can do work with broadly as well. So we have this. So the way our technique, our model works is that it takes this graph, which is this temporal interaction network, and our model is called Jodi. What it's able to do is to generate these embedding trajectories for each node. So typically you may be familiar with embeddings, but here we extend those embeddings to say these are trajectories. So the embeddings change from one point to the other, as is shown, right? So as interactions happen with this item representing a movie, its embedding shifts from here to here to here, right? So we get these dynamic embedding trajectories, which are way more informative, because it encodes the temporal information. It is way more informative than the static version, than their static counterparts. So the way the Jodi model works is, and Jodi stands for Joint Dynamic Interaction Embeddings. It is a mutually recursive recurrent neural network framework, which has two components: an update component and a projection component. The update component has a user RNN, which updates embeddings of users, and there's an item RNN, which updates embeddings of items. And there's a projection component which forecasts or predicts what happens in the future. So using this Jodi model, we are able to use that on real-world large-scale data sets that we created and made publicly available from Reddit and Wikipedia, and a few other data sets as well. And these are like relatively, reasonable size data sets, I would say, not super large, but reasonable size, where we had the ground truth of which accounts on these platforms are good and which accounts on these platforms are bad. So using this Jodi model, we were able to outperform existing models by around 12%. This particular style of model has since then been extended and used at Meta for their TIES model, which is temporal interaction embedding model, very similar. So they were able to scale it up. They made some simplifications to our model, and they're able to scale it up to super large network, to the Meta scale or Facebook scale systems. So all that to say that, dynamic graph based models have a lot of value to be added over here. Again, I'll pause here. If there are questions, happy to take them. If not, I'm happy to continue.
Yes, Srijan, I have a couple of questions. I mean, one was on the previous part. So when you talked about multimodal, did you just use image data to augment the text, or audio and video as well? And the second question is more related to the work that you're doing broadly. Yes, you're doing excellent work in terms of detecting malicious actors and all. But one thing is, I mean, how fast do the detection algorithms evolve versus how fast do the people who create this malicious content evolve? So what is your take on is there like a difference in the pace at which the research is accelerating versus the pace at which the malicious content is moving?
Absolutely, great question. So the first question was what sort of modality do we use in the first part? We use image modality because that's the data set that we had. But today, there are more sort of multimodal data sets that are available. So you can do equivalent works with, video data. We just released very recently a YouTube data set. So if someone's working on YouTube or video based information, they can check that out. So that particular work, the work that I presented, that's only for image. The second question is, bad actors co-evolve with detection technology. Who is faster, and how do we keep pace with it? So I always say that it's a cat and mouse game. As you will improve the detectors, the bad actors will also improve, and vice versa. So it's an ever evolving game. So actually, in one of our one very big line of research that my group has is the adversarial robustness of these systems. To know how robust, how reliable these systems are under adversarial attacks. So the hypothesis there, and I'll talk about some of the adversarial work that we have done, is the hypothesis there is that when you have a lot of adversarial adversarial actors, uh, you can either wait for them to evade your system, or you can simulate how they might potentially evade your system, how they might break your system, how they might change their behaviors, and you can then expect how that system would evolve, and you can essentially predict those, or you can create systems that are more robust against these adversarial attacks, right? So a very big part of our research is this adversarial behavior, and which I'll talk about in like after I
So,
want to.
do you think is there some sort of an equilibrium in terms of how this game evolves? I mean, detecting the putting the detection models versus how the bad actors evolve. Is there some sort of an equilibrium we're going to get into?
I am not aware of like any game theoretic approaches that people have tried to model this in the theoretical sense. So I'm not able to say whether there's like an equilibrium, but I can say that it's an ever evolving scenario, ever evolving game, infinite game, if you will, right? So where like yeah, the detectors are ever evolving as well as the bad actors are ever evolving.
Okay, yeah, thank you. Yeah, you can proceed to the next one.
I see there's a question on chat says, how
Yeah.
exactly does Jodi model detect the anonymous or malicious users? What kind of algorithm are used to identify them? If there's a anonymous, so I mean, the data that we have on Wikipedia and Reddit and so on, like naturally they have the usernames, but for our experiments, we strip out all that information. We only look at the anonymized version of the data. That said, I think like what you are asking, like the assumption here is that you have in these data sets, the assumption here is that to be able to create a graph that has some value, each account or each user should have more than one interaction. That's when, graphs have value. Um, I think maybe, and please clarify if my interpretation is wrong. What you're asking, my interpretation is that you're asking if each account only has one post, right? Because that's what an anonymous account means. Like what do you do, right? In those cases, I don't think like graph-based models are the best ones to do. Maybe you look at like NLP-based models to detect them, or even if you have like anonymous accounts on social media platforms that are each account making multiple posts. Uh, Again, what we have seen is that their identity is less valuable in detecting whether someone's good or bad, but their actions, their behavior, their actions, their temporal signatures, their who they interact with, how do they interact with, all of that is more important in terms of detecting whether something's malicious or benign. I think there might be one more question. Seems not. Okay. All right. I'll talk about one more detection work. And this kind of also relates to what Shrikar was asking earlier, right? Like bad actors change their behavior. They can always be smarter than the detection models. And in fact, not like that's a very pervasive problem on Wikipedia, where once you ban an account, there are like hundreds of other accounts that a bad actor can create. And in fact, they have released some data sets, some statistics where some accounts have created some bad actors have created 500 plus accounts on the platform to inject their point of view, their biased point of view on Wikipedia articles, right? So ban evasion, regardless of ban evasion is a very big problem, right? And what one can do is to either think of these different accounts being banned or detected as malicious as being independent, or you can think of them as a group, or you can think of them as what we call sock puppets, right? Where sock puppets are multiple accounts being secretly controlled by the same entity. So we created the first ever study around ban evasion in a data-driven manner. We collected all data from Wikipedia, which had this data publicly available. We cleaned it massively. We identified these ban evasion pairs, which are like when one account is bad, is malicious and is banned, a new account is created and it is also banned eventually, right? So we looked at these ban evasion pairs and we created detection models, again, looking at language as well as temporal and other behavior attributes. And we were able to create like super high performing detection models, including prediction models, right? So what this means is that there's hope in terms of creating these systems that are not only reactive, but also proactive, where when a new account is created, you can kind of estimate its probability of it being a ban evasion account of an existing banned account. So we are now actually working with Wikipedia moderators to create a tool where they can use this system as a guiding point to better detect and attribute ban evasion, which is something that they really want to do, but right now they're doing all of that manually, right? So the type of tools that we develop, the type of models that we are developing, they're not only academically valuable. I mean, we write a lot of really good papers at topmost computer science, machine learning, AI conferences, but it also has a lot of practical value, and we can really reduce the burden of, in this case, Wikipedia moderators. So far, I've talked about multiple papers, 3 papers to be precise, around detection. So on multimodal, multilingual, graph, as well as behavior-based models. And all of these are great, but as Srikar was saying, these may not be robust enough to adversarial actors or malicious actors who are trying to break these systems. So we have a very huge line of research in my group, where we're looking at the adversarial as well as natural robustness of these detection models, of LLM models, and so on. And I'll talk about a few. So the Priyanka is asking, are there any specific aspects of ban evasion detection? I'm assuming you're asking about the detection model and not the type of evasion that's happening. So assuming that that's your question, the type of detection models that we are working with over here is a very, I would say, relatively simple model, but it works very well. So it's a random forest classifier, which has a bunch of different features around text, around time, around graphs, and around behavior of these accounts. And it's a binary classification task in an unbalanced data set. And we use that to do multiple different classification tasks around detection, around attribution, around clustering, and so on. So you can look at the paper. The paper is on my website, as well as if you take a screenshot of this, you can find it very easily. And the data and code and everything is also available online. Cool. So let me talk a bit about robustness, which is super crucial because, we had been thinking about, so I mean, I've created a bunch of different detection models over time, but we started thinking about like, how robust are these detection models? And we wrote a paper specifically studying that on how, if bad actors know that there are these models that are being created that are trying to catch them. So if they are trying to manipulate these models, how well are they able to do that in a way that would, how easily are they able to do that? Right. So the research question we asked was, are detection models, both academic as well as commercial, vulnerable to adversarial manipulation? And what we did was we created this benchmarking, robustness evaluation and benchmarking suite, where you can evaluate this adversarial robustness of these detection system, including we also investigated the adversarial robustness of Meta or Facebook's bad actor detection system. So the way we did that was we created a adversarial attack simulation system called adversarial text generator called PetGen. And this work was funded by Facebook. So the idea behind this is that, let's say, these Jodi style models, these sequence style models, they assume that a user is represented as a sequence of actions or posts, a sequence of actions that they have taken or posts that they have created or interacted with. So each of these each account can be treated as a sequence of posts, and these posts can be of, let's say, different topics. And when you pass it through a sequential through a classifier, let's say the account is malicious and it's correctly identified as malicious. But someone can create an adversarial attack on it, a bad actor specifically. And let's say, and we want to simulate that through an adversarial setup using our system that we create, is called PetGen. And the idea is that, let's say, using PetGen, you create a new post for the same user. So you just add a new post. In such a way, can you add a new post in such a way that when you pass this sequence through the same classifier, it detects that it says the user is not malicious, but in fact it's benign. If we are able to fool the classifier in this way, then we can say that the attack is successful. And our goal is essentially to be able to achieve that in an optimization framework, where we have this PetGen or personalized text generator that generates this post in such a way that it's able to fool this pre-trained classifier. So PetGen is this attack post generation model. It's very super, like it's super, it's a model that takes into account a lot of different attributes about each user. For example, it takes the sequence of posts that they have written and the context of each of these posts. And PetGen has two stages. It has a sequence-aware text generator, as well as a multi-stage, multitask fine-tuning and learning framework. So let's say we say that we want to generate an attack post on the topic of soccer, right? So what we'll do is we'll do temporal we'll do attention. We'll calculate the attention weight between the similarity of the target context and the existing context, and then based on that we'll take the post and pass it through the sequence-aware text generator, which generates an initial version of the attack post, which will then fine-tune in this multi-stage process, where we want to make it relevant to the recent post that the user has made, make it similar to the style that the user has, make it relevant to the context that we want it to be in, as well as ensure that the resulting post is able to attack the detection model. So once that happens, we are able to generate this attack text. This is a model that we train. So the training part, the subparts of this model that need to be trained are this and this. And this was an RNN-based framework, because at that time, that's what people were doing. And in this particular framework, we are able to generate this attack text, and doing that in a way by treating this this detection model as a black box. And we are able to do a lot of experiments, and we are able to show that we are able to fool even Facebook's detection model in a sandbox setting 1 out of 4 times by this attack system, right? And we did a lot more experiments. I don't have all the results over here, but you can look at the paper for more details. But the idea behind this is essentially that we are able to create these systems that are able to understand how robust these detection systems are, right? And if these are detection systems that can be fooled 1 out of 4 times, then that's not great, especially when these types of systems are being used to serve millions of users every day on platforms like Meta, right? So since this work was funded by Meta, and it was independent, like they were not involved in the research, they just gave funding through a Facebook faculty award. We made them aware of these vulnerabilities that their system had, and hopefully they took some action based on it. And we did a lot more experiments using publicly available detection systems, including systems like Jodi, and we created these attacks And since this paper has been published like now a couple of years ago, we have written many more papers along these lines of adversarial as well as natural robustness. So we have a couple of papers at ACL last year and EMNLP the year before, where we're looking at the adversarial robustness and natural robustness of multimodal models. In those lines of work, what we do is we try to say, if you have a multimodal model, and now we're talking about the state-of-the-art multimodal models that are there. If you have these multimodal models, how robust are they to various different types of natural input perturbations, as well as adversarial inputs that might be there, right? So we do a lot of these adversarial as well as non-adversarial analyses and find various sorts of vulnerabilities that these multimodal systems have. And you can, if that's of interest to you, you can look into that particular line of research on my website.
Okay, Srijan, I have a quick question. So, PetGen is one way of creating adversarial content. So, did you compare it with other ways? Because malicious actors do not use only one way to, evade the content. So, is there like a list of ways in which they evade content, and how robust is your system to those ways?
Uh, I wouldn't. Okay, yeah. So in the paper, of course, since it's a peer-reviewed paper, we had to get we have baselines. So we did compare it with at the time the state-of-the-art attack systems that were there, attack models that were there. Field has evolved since then. Way more attacks have been created, and I would say that I would not treat any one of these attack systems as being like the go-to system for a bad actor, right? A good system, a good bad actor, let's say detection system, should be robust to all of these detectors, right? It's not a matter because all of these detectors have some pros and cons. They're looking at it from various different ways. PetGen, for example, generates text. There are some other systems that generates. So PetGen, for example, generates an entire post. There are some other papers that generate comments, for example. There are some other papers that look at the graph, right? And bad actors are able to do all of those things. So a good detection system should be robust to not one, but all of these different types of attacks, right? So that's a very, very high bar for these systems to achieve, but they have to do so. So defense against adversarial attacks becomes even like that's the next step, right? So the PhD student who led this work now is working on a journal version of the paper where he's creating essentially some detectors around, or rather creating robust detection models, right? That are robust against these. And one way to do that, and that's the way he's approaching it, is to do adversarial training. So, when you have these attacks and you know that some of these attacks are successful, you can use that as training data or fine-tuning data to improve the detection model itself so that it's not at least vulnerable to the same set of attacks. Now you can imagine that when you are doing that, you can have, let's say, 10 different types of attacks. You can have PetGen as one of those 10 attacks. And you can create a lot of these adversarial samples that fool the detection model and use those adversarial samples as input to do adversarial training of these detectors to create the next generation of systems that are robust against these types of attacks, right? So we're looking at these attacks from both the adversarial side of attacking as well as from the defense side. And I think that's something that, and again, right, you can continue going on and on and on, right? Like you can attack the adversarially trained model as well and create new attacks. And so I think it's an ever evolving situation, and it requires not only this sort of AI feedback that's happening, but also human feedback, right? So humans can also create these attacks, you can, so for example, red teaming is a very standard thing right now. When you look at like these types of systems or even large language models, and that's a human way of trying to break the system, right? So I think it's super important to understand how robust these systems are, and not only these systems, right? Any sort of like impactful system, including large language models, should be like their robustness their reliability should be accounted for.
It looks like there are two questions as well that have been posted by some of our participants.
Mhm.
The first one says, "How exactly does the Jody model? How exactly the Jody model will detect anonymous or malicious user?"
Rami, I think he already answered those two
Oh,
questions.
yeah. I'm sorry about that.
Yeah.
And the second question as well, has that been answered as well?
Yeah, the second one as well. Yeah.
I answered both of those. Yeah.
Okay,
Yeah.
sorry about that. That's my
No,
fault.
no worries. Yeah, thanks.
I just saw them there. I'm sorry. Keep going. Please go.
No worries. Yeah, if there are more questions, please feel free to post them and we'll be happy to answer those. Cool. So I will take 5 more minutes and then we can open the floor up for broader questions if there are any not related to my talk. Yeah, so we'll talk about some of the mitigation work that we've been doing. And there we are working with on multiple different threads actually. So this work around that we started looking at like COVID misinformation. Of course, we started doing this work right when COVID hit, so March 2020. And what we did was we collected a lot of COVID tweets. At the time, people didn't really know that a lot of COVID misinformation is going around. So we were collecting tweets to do interesting analysis. We didn't know that we wanted to study misinformation at the time. But eventually we realized that there's a lot of misinformation in this data set that we have collected. But at the same time, there's a lot of counter misinformation. So just like a lot of people were spreading misinformation, a lot of other people were correcting misinformation as well. So we got interested in looking at this aspect of correction called social correction or peer correction, where it means that non-professionals and non-organizations are involved in doing the correction or at least spreading right information. So things like, garlic cures COVID-19 was a very, very popular thing at the time, right? And people were posting that. And even and that was like, I got WhatsApp forward messages from a lot of my family members around like those herbal and, these garlic and other things curing or protecting you from COVID and so on, right? So while a lot of that misinformation was being spread, there were a lot of people who were countering it. And in fact, we did this analysis where we looked at 8 million COVID-19 tweets. We created classifiers by doing a lot of hand coding of data. We created misinformation as well as counter misinformation classifiers. And we created these counter misinformation classifiers and ran it on all the 8 million tweets. And then we categorized on whether that's coming from ordinary people or from government organizations or professional fact-checking organization and others. So when we did that, we found the staggering statistics that 96% of all countering messages were in fact from non-experts, right? So that essentially explains the role of this crowdsourced, in a way, counter misinformation effort, which is super important because now you have like a huge part of this effort being heavy lifted by ordinary users like you and me, right? So this work was an early influencer to Twitter's Birdwatch, which has now been renamed to Community Notes. And the Birdwatch system essentially is this platform where anyone can write fact-checking messages, right? So it's a crowdsourced fact-checking platform within Twitter, and it's gotten very, very prevalent and very prominent on the platform. So our work essentially, I would say, helped guide the idea that yes, counter misinformation is already happening in an unstructured manner by ordinary users. And since then, we have also looked at the robustness of Twitter's Birdwatch system as well. And then last year we did this work where, and this was pre-ChatGPT, what essentially we did was we said, okay, can we use like these text generation systems to write counter response messages that correct misinformation, right? So for example, if someone's tweeting misinformation that, COVID vaccines alter your DNA, and we realize that normal people, ordinary users who are writing counter responses, but not in a polite manner. They're saying you're born to speak nothing but lies. what our system does is essentially, replies in a factual manner what these counter, with counter response messages, right? So that's like we wrote this paper. Think of it as like ChatGPT for counter response generation. We did this work way before ChatGPT was popular, but now it's very like now no one gets surprised that, oh, you can generate content that is factual, right? Like, no, now it's so commonplace. I use ChatGPT like 10 times a day, right? So I would say that but this paper essentially showed that these generators can be used, text generators can be used for societal good as well. I think yeah, thanks. I'd like to wrap up my talk by thanking the students, postdocs, research engineers that I have in my group, as well as the sponsors, broader sponsors of my research. Happy to pause, take any questions that you might have. And yeah, broadly, today I talked about three aspects of my research around web integrity, looking at detection models, robustness of these models, as well as various different mitigation strategies.
Okay, thank you, Srijan. There is one question from the attendees, which is, what are the ethics that Jodi model will follow? Again, I'm not sure if I understand the question, but
I don't quite understand the question as well, but let me take a stab at that. I think what's being asked is there bias in Jodi model, right? What sort of yeah, if what's the bias, let's say, right? That's a part of ethics, I would say. Jodi model is trained on the data. So any detector, for that matter, is trained on data that has on data that says, here are accounts that are benign and here are accounts that are malicious, where these malicious accounts were either identified manually or by previous systems and so on, right? And these systems, these good versus bad, benign versus malicious data is used to train a detection system. So any bias in that original data that's there will be learned by any system that's trained on that bias data. I don't think I'm not familiar with any work that has systematically looked at whether there are biases in categorizing bad actors, right? There might be. I'm not saying there's not. I don't know. I don't know whether there is any bias in the data itself. But if there is, then any detector that's created on those data sets will have those inherent biases in them, right? And I think it's an interesting research question to debias and de-risk these detector systems so that they are not biased against, let's say, certain communities, certain demographics, and or on certain topics, right? So I think it's debiasing of detectors is definitely very important. Yeah, so that's my interpretation of what your question is, but feel free to correct if our interpretation is not right.
Okay, thank you. So I have a question too. Recently, there was a study in my field of MIS where they actually did a lab experiment where people were asked to, use ChatGPT versus Google to perform the same task. And what they found is, for the same set of tasks, the answers that ChatGPT gives, people perceive it to be of higher quality and more accurate than the ones that Google generates, the search results, even though they're factually wrong. Right. So broadly, my point here is, while these machine learning systems to detect all of these are great and they are useful and we definitely need them, there is that human element of how we perceive what is misinformation and what's not. So how can we kind of, merge that human element of how the human psychology and how humans perceive misinformation with what you're doing, right?
I think that's very important, right? My research is very interdisciplinary or transdisciplinary, right? But that's very important. In fact, the human component is, I would arguably say, is as important as the non-human or the technological component over here. In one of our very early works, when I was a PhD student long time ago, we looked at the study where we said, okay, we gave people 2 pieces of Wikipedia articles. I mean, I was looking at Wikipedia at the time. We gave them like one fake article and one real article, and both were like on Wikipedia. And we said, one of these is fake. Can you identify which one it is? And if it's like 2 options, so random guess would be 50% accuracy. Humans were able to get only like 66% accuracy. Like 2 out of 3 times they were right, 1 out of 3 times they were wrong. Even despite telling them that your task is specifically to find misinformation here, right? And then we looked at the error analysis, right? When were people giving wrong answers? And we found that people very much give a lot of importance to the aesthetics of the article, right? If the article has an image, it's more likely to be true. If it has sections, it's more likely to be true. If it has even if the image is wrong or even if the text is wrong, right? Like they don't care. So there's a lot of human psychology that goes behind this, and that's very true for LLMs, right? You're absolutely right that people are way more trusting of generated responses, AI generated responses, than they should probably be, especially when hallucination is not under control, right? It's even worse, I would say, when the response is like partially correct, which is what these LLMs do, right? If something is like obviously wrong, then people are not going to believe it, right? But the quote unquote beauty of these LLMs is that they write it in a way that it seems it's correct, but in fact it's not. So I think solving it from the technological angle, that yes, these LLMs should be more factually correct. They should be guardrailed. They should not hallucinate. And there are a lot of other issues as well, that they should not generate toxic content, or they should be free from prompt injection and so on. A lot of things are there. While there's a lot of like technological aspect that should be there, uh, people also need to be more aware. And I think there's no solution panacea that I have to say that, okay, this is how we can make people more aware of these things. I think it's more of like, um, like people learn by doing mistakes, right? So I think that's eventually what's probably going to happen.
Okay. Okay, thank you. Are there any other questions from the audience? Yes. Any last questions? Okay, so it looks like there aren't any questions. So on behalf of the FedEx Institute of Technology and University of Memphis, we would like to heartfully thank you, Srijan, for your excellent talk. You have enthralled our audience. And so thanks a lot. And so now we will give you back your valuable time. Okay. Okay, thank you.
Yeah, thank you so much for inviting me. It's my pleasure to be here. And yeah, if you have if you are interested, you can connect with me on LinkedIn or reach out to me for any further questions or inquiries. But yeah, have a great rest of your day.
Yeah,
Thanks,
okay,
everyone.
thank you.
Thank you.
Thank you. Bye-bye.